So I want to draw your attention to the similarity between AGN disks and protostellar disks, because I have room for friends who have worked in areas on star formation, especially on protoplanetary disks. And I want to draw your attention that there is a huge amount of gold mine to dig out of AGNs along the same line. You don't have to move very far. Here, if we just move out from your favorite star forming region with disks on scale of molecular clouds, and eventually into the areas of galactic center, and where you see a lot of stars, young stars, going around the center to a very active region of AGNs. And so now, what are the similarities? And we all know about planetary system. Well, the mass ratio between the planets and the central star is somewhere between 10 to the minus 6 or 10 to the minus 3. The period lasts for days, and the radius to the semi-major axis ratio is about 10 to the minus 4. In the galactic center, very similar type of mass ratios are also present. You have stars like stars around SAGA, the S stars, and the disk stars. Their mass ratio to the central massive black hole is supported 10 to the minus 6 to 10 to the minus 3. Their period is on years to millenniums, and their radius and of physical radius of star to their semi-major axis is supported 10 to the minus 5, similar to the planets. And if you look at, as I will try to convince you, that look at disk structures around these guys, and they have similar aspect ratio and maybe slightly different gravitational stability parameter, and the persistent timescale is even similar. And so what we need to do is to try to figure out what is going on. AGN research has come a long way from many different wavelengths and many different surveys and various other things. The key issue of that you want to know about AGN and all along is the mass of the central massive black hole, the accretion rate, and things like the conversion efficiency and the Eddington ratio. Now, over the years, there have been large surveys such as the Sloan Digital Survey that gives you, a huge amount of data. From those data, you can construct luminosity functions and at different redshift, and you see there's a general evolution of this luminosity function. And you can also work out from their luminosity and the signature of black hole mass, you can work out things like the Eddington value. And so the idea here is that you can get an accretion rate. You can compare this accretion rate, because the luminosity function has evolved in time, you can construct these population synthesis model. What I'd like you to walk away from this vast amount of work by a huge number of people in the last 20 years is just with two numbers. One number is that the efficiency factor of converting accretion energy into luminosity, the rest mass energy into luminosity. And this is what is called the efficiency factor. It's typically somewhere about 0.1. And plus minus, there's a spread, and depends on who is doing the determination. The other is that you can relate the accretion rate with the m dot of Eddington limited m dot, namely the value that you would get if you convert everything very efficiently, and that the radiation pressure would start to become comparable to gravity. So, and once you get these two numbers, and then the problem is starting to become relatively easy to resolve. And the other issue that one needs to worry about is and we only see 1% of the galaxies are in this AGN phase. Is it only 1% of galaxies that's always on, or alternatively, 100% of the galaxies is on for 1% of the time? So this is the issue of duty cycle, and one can even get some ideas about the duty cycle to eventually infer the active phase. So the active duration of AGNs is typically a few times 10 to the 8 years. And when they are not active, they are DGMs, dormant galactic nuclei. So 99% of the time they're spending on dormant phase, and about a few percent of the time they spend in this active phase. So what can we learn about this kind of active phase? And so people have constructed models, theoretical models, and they try to give you a cartoon picture of what's going on. And the cartoon picture tells you that usually there is a central massive black hole, and within the very central region, maybe there's a little cavity with some jets that's coming out, and it's very similar to star formation problems. And then you have relatively thin disk and extend out to maybe the region where there is some disk wind is launched. And these winds are moving at speeds of several thousand to 10,000 kilometer per second. And so this is called the broadline region. And then even further out, you may have what is called the narrow line region. And so this is the standard picture, and I'm going to elaborate a little bit more on this picture. And the scale that you're looking at, the most natural scale, is to scale it in terms of the gravitational radius, and you go out in terms of log gravitational radius, and as you expand out, and you see what occurs in this general region. And and if in most of the cases, we try to develop a very crude standard alpha disk model where you can approximate the structure with approximate the viscosity in terms of parameterized form, and so-called alpha viscosity. And once you've done that, and you can explain or you can express the accretion rate in terms of this surface density times the viscosity. And then the key parameter here are three things. One is the so-called alpha parameter, and that is the efficiency of viscous transport, and the other is this aspect ratio and thickness over radius, and the third is this gravitational stability parameter. And in a steady state, since you already know from the previous slide in here, which I already talked a little bit about the m dot in terms of the efficiency factor and m dot in terms of Eddington factor, you apply all of these things in, you can get into a relationship, a single relationship between these parameters, such as alpha, aspect ratio, and Q, and for a population of AGNs. And that turns out to be very useful, and everything can be worked out in terms of the mass of AGN divided by 10 to the 8 solar masses, and the radius that scales with parsecs. Okay, so what you will find is from this kind of relationship, you don't go very far before the disk become gravitationally unstable. And in fact, you go out to something like 1,000 gravitational radius, which on the scale of, for a 10 to the 8 solar mass black hole, we're talking about 0.01 of a parsec. And you're already getting the disk become gravitationally unstable. And in these gravitationally unstable disks, and you tend to find, you tend to form either spiral form, if it's very cold, very pronounced spiral form, or if it's marginally, warm, and you can actually form these fragmentary small pieces. And many folks in the room have worked on this, including my namesake. And so those are theory. How do you link this theory with observation? And it's all very good, as Paul would say, that theory is all talks. And let's see if we can get some link to reality. And one way to do that is by looking at what is called the reverberation map. And many of these AGNs are very active. Their lights fluctuates, and when the light fluctuates, and the light that is on the lamppost has a tendency to shine throughout the disk, and with some time delay. Because of this time delay, you can actually start to map out by looking at different wavelengths, and you can map out the structure of the disk as a function of radius. And these fluctuations are usually associated with X-ray fluctuations with corona. And if you look at the very short wavelengths delay, they're hours, and you will map out the innermost region. And whereas if you look at UV and visual and eventually infrared, and you find that you're probing to light days, light weeks, light months, and light years. Okay, so there are lots of these type of data, and all the way from X-rays to optical to UV. So I've been working together with an ex-student, Jiamu Huang, and also with Keith Horn on one of these campaigns, which centered around NGC 5548, and that had several days of HST data. And so then they were able to reconstruct a time delay, and so they can see that at different wavelengths, there is a delay in terms of days. And for example, there are delays if you're going out to the relatively long wavelengths end, and you're talking about delays of several 4 or 5 days. And at the same time, one can construct their SED, and these are SED that looks almost like the classical Titori type of system. And from these, and the SED, of course, changes between the high state and the low state, and as the light propagates from the lamppost to different parts of the disk. So, and the time scale for this is so short. These are light travel time across the disk, and there's no time for the structure of the disk to respond. So it tells you that the outer part of the disk during the high state, large fraction, 80 or 90% of the luminosity come from the reprocessed radiation, not from the viscous dissipation. But nevertheless, we can start to map out by matching both the SED, the form of the SED, and the time delay at different wavelengths. We can start to probe a structure of the disk, and these structure have either a wavy-like structure is one type of model that we can generate, and so you can shine onto different parts, And so you can reproduce both the time delay and SED properly. Or alternatively, you can also have a alternative model that when the light shines, it eventually has a very thin disk and then meets into a region which is relatively thick. And this thick disk happen to be close to the region where these broadline regions are launched. One possible cause of this is that this is also the region that temperature near the surface, at least, drops down to below the sublimation temperature of silicate grains, and therefore they start to condense and to enhance the opacity, and then their Eddington limit of the disk start to be much reduced, and you start to feel the radiation pressure, and that tends to launch this so-called wind. And once they get exposed into the surface area, their temperature may go up again, they may evaporate. And so this is the kind of physics that we're still contemplating. In any event, the aspect ratio you tend to deduce from here is something like about 1% or so out to the location of something like 10 to the minus 2 or thereabout parsecs. And so it's very thin disk in the inner region. And with that thin disk, with that kind of temperature, with that surface density, and so on and so forth, we can infer that the gravitational stability parameter is order unity. And and they extend out to this region. So it is very natural to ask, how can we maintain the gravitational stability parameter to be marginal over such a long extended region? Now, so here is just some theoretical calculation that one can show that this gravitational stability, in fact, plays a role, but I won't go through that. And one can also do some detailed calculations on these structures. And if Q is maintained and marginally of order 1, what would you expect the aspect ratio to be? And they're not far from what you see in the reverberation map. Okay, so from this kind of analysis, one can work out things like the density and sound speed in this part of the disk. Now, the density is relatively easy to get because if the disk is marginally gravitationally unstable, the density is just like the average density of the black hole at that radius. And so you can work out what that would be. And so these are quantities about the disk structure, which are very useful, as we'll see. But what is also very revealing is that the temperature one gets from here, you get a sound speed because you know the aspect ratio, and you can translate that into a temperature, and then you can work out what would be the effective temperature on the surface. The effective temperature will give you a effective temperature that looks different from the standard viscous accretion disk. And you shouldn't be surprised because part of it is being irradiated. And but even during the low state, when it's not being irradiated, and it would still depart from the standard accretion disk. For many people who had worked on protostellar disks, and they love to do the SED fittings, and there are standard accretion disks with effective temperature and composite black body. But it seems that in order to maintain this marginal self-gravitationally and stable disk, that you need extra component of the radiation, as you can see from here. And this is called for when people actually observe, and they indeed see the observed SED has excess, considerable excess, even compared to standard viscous accretion disk. So then you can go back and consider theory. What is theory is that if you have the radiation from the surface, then what is the energy source? So the energy source has several different quantities in it. And this is Q plus due to viscous dissipation. And this is the last term is associated with irradiation. So in star-forming disks, that's all we need to worry about. But in AGN disks, they may contain stars that will produce their luminosity. And they may actually, these stars, if they evolve off the main sequence, they can produce supernova that could also heat the disk. And finally, the supernova remnants may be little black holes that's inside the big black hole, and that can accrete, that can also produce luminosity. Can we analyze each term by term? And that's what I have been doing in the last 5 or 6 years, and be focusing primarily on this. Now, first of all, let's look at what is the stellar heating. The stellar heating is going to be something like the stellar surface density, the number surface density of stars multiplied by their luminosity. Of course, one should integrate this over all different masses, but as I will show you that, in fact, that one important aspect of AGN disk, the star-forming region, is very different from the standard in GMC, is that they almost have a peaked uniform mass, and they're very top-heavy, and they have a uniform mass, and they have at any given radius, you know what that mass is. And in addition, these stars, they are not like normal standalone stars, and these stars actually interact with their embedded disk, and they accrete and they decrete, and so they undergo metabolism. And and that process itself is what I want to talk about. And the star formation rate is just related to this kind of surface density, and divide by the duration of each star. So it's a self-regulated process. If the lifetime is short, and when one set of stars goes away and you form another population, but some of the stars may not go away. They may actually be massive, and they may become immortal and live for a long time. And we will come to that in a few minutes. Okay, so the stellar luminosity you can work out in terms of both the nuclear energy generation, and plus there is a accretion and the wind luminosity, both in terms of generation and loss. And the mass evolution of individual stars, because they're not in isolation, they accrete, and but they also generate wind, and so they can also lose. And it's a balance between these two that determines the rate of mass change. And the accretion rate, one can start with a standard boundary accretion rate, but in fact, in the disk, all the issues about accretion after you open up small gaps also play a role. But in addition to that, the accretion may become so fast around these massive stars that the stars start to become very massive. When they become very massive, they can produce so much luminosity, they can reach the Eddington limit. The massive stars are very close to the Eddington limit. When that happens, the the effective mass of the individual embedded stars is reduced, so the accretion rate is reduced. In addition, you have the winds. The more massive stars tend to be much more, produce much more intense winds, like Wolf-Rayet stars, and those must be taken into account. So, and this is a picture that I would like to present to you. In addition to star formation, there is also the possibility of star capture. And in around every AGN, around every galaxy, there is usually a supermassive black hole. And around every supermassive black hole, there usually is a nuclear cluster of stars. The AGNs occur when the supermassive black hole is surrounded by gaseous disks, and these stars would tend to pass through these disks. And when they do, they feel a little bit of drag, and they settle into the disk, and they grow. And so you can work out the common occurrence of these clusters. And this is a paper by Cormedy and Ho, who had compiled enormous amount of data, and to give you some indication about what we learned about the individual stars. So you can calculate the capture rate, and the capture rate has been developed, and this is similar to some of the capture rate you would expect to see if a planet is moving around a host star, and it go in and out of the disk, and one can calculate these drag effects and try to figure out the time scale for them to settle into the disk. So, and those time scales are comparable to the star formation time scale, and one can work out this kind of rate. Okay, and since today we know a lot about nuclear cluster, we can go to places like the Virgo cluster, and we can look at the central region, the surface brightness profile, and we also know and sigma relationship of black hole with their surrounding region. So we can work out the capture rate. And so here is a cartoon picture. You can have star forming in the disk. You can have stars that get captured into the disk. And what I want to say is, once they form or capture into the disk, and their fate is going to be the same. Namely, that they will start to accrete, and they will start to grow until they're about 1,000 solar masses, and they will rapidly evolve. And so let me go on to look at how they evolve. Once they're in the disk, they're just like accreting, protoplanets, and they can open up gaps. They can, or alternatively, when they're relatively low in mass, and they can perturb the flow around here. So this is there's been tremendous amount of investigation on this problem in the context of planets, and it's easy to extend that computation to look at the problem around AGNs, and with a very able graduate student and Yixian Chen, and also Yaping, Li Yaping, and we've been working on and both 2D and 3D accretion problems in the context of both planet and AGN. So one can work out this, and then you can look at the possibility of getting stellar winds, and how this stellar wind may be able to give you very intense radiation. Usually this only occurs when you're very close to the Eddington limit, when you're far away from the Eddington limit, and you have line-driven winds, whereas when you get close to the Eddington limit, you have the continue-driven winds, and these winds can be very efficient. So under some circumstance, you can look at the wind loss rate as function of the mass, and the nuclear energy or the accretion rate you can work out in terms of red. And when these two, black and red, matches with each other, you have an equilibrium. Namely, you accrete as much as you shed off through stellar wind. Now, and this type of process is, you would have thought, really this will contradict each other in the sense, yes, it indeed does. And as I will describe a little bit later, that on the one hand, the radiation from nuclear burning actually try to push material away. On the other hand, the gravity of the star pulls in. So when they are matched, they get into an equilibrium. Now, what is interesting is there is a work that is done with Matteo Cantillo and try to look at the evolution of these stars with a MESA code, MESA stellar evolution code. And we find that these, under some various AGN environments, these stars can grow to close to about 1,000 solar masses. And then they stall. And they don't grow any further, and they last forever. And we call them immortal stars. And why are they immortal stars? And the reason for that is because when they accrete, they get fresh supply of material and from the disk. And if this fresh supply of the material can get all the way down to where the nuclear burning takes place, and then you can resupply the fuel and take away the byproducts. And this is very much like what we do every day with our own metabolism. We eat and we get rid of the waste, and our weight is about the same. And the stellar mass can do the same, and they can, if they get into this state, they can live forever. Now, if they live forever on the main sequence, and what happens is that they consume primarily hydrogen, and hydrogen goes through a burning. But mostly, this burning occurs around this region. You can have some carbon CNO burning, and then the burning will start to take place and convert hydrogen into helium and generates helium. So the byproduct on the main sequence is only helium. So whereas the internal mixing is sensitive, under some conditions, you can have a fully convective star. Under some other conditions, you may have part of the radiative star. And this will make a difference because you can work out the rate, how much you're going to convert hydrogen into helium and the helium production rate. So, so with this star, since we now know that its luminosity, whenever you start even at very small mass, they will always grow to be of order several hundred to 1,000 solar masses for that particular region. Further out, they produce a slightly less massive stars. And you can work out this in terms of that to balance the AGN disk cooling rate, the radiation rate, with the number of with the luminosity of individual stars, and then you can work out the surface density of these stars. And you can also work out the total number of coexisting stars, and out to the radius of a parsec or so. You can have several hundred of these supermassive stars, and you can work out what their implication of their coexistence is. And if they evolve off the main sequence, and then they will have a limited lifetime, and you can even work out the rate of star formation. So now all of this is a fancy story. Is there a way we can test this idea? This the test lies in looking at the spectroscopy of AGNs. So if there are these forever stars, and then they tend to only produce helium through the CNO cycle, and the helium production rate in the AGN lifespan, and they live for about 10 to the 8 years, as long as AGN is active. So they typically will produce 30 times of their initial mass, which is, so per star, they will produce something like 3 times 10 to the 4 solar mass of helium. And then you can work out the helium enrichment rate in the disk, because you know the surface density of these stars, you know they will last so long, and then you can work out per individual, they come out with this much. So you can work out the rate of generation of helium pollutants. And then you can plug into the standard diffusion equation for viscous accretion disk. This is the same kind of equation one used to understand the diffusion of dust grains, as well as different elements. Here, the important issue is that you include these sources, and they will get added onto these disks. And I will tell you that this is very important to consider this effect when we look at the overall picture in a minute. Now, so how do you measure this helium content? So you measure the helium content by looking at the spectral lines, and here is a typical AGN line and with some helium content. And you find that in these lines, typically the helium abundance is less than 50% higher than the solar value. So it's never that big. So that means that the amount of helium production is limited. So the number of long-lived stars, which we have predicted, is probably not there. And it could not have done this much damage to the this much pollution. So how do we get around to that? You know, a good theorist never give up. And when you see there's a problem, you say, how do I get around the problem? Is I make these stars evolve into post-main sequence. But you say, wait a minute, you talked about this metabolism refreshing supplies, and how do you get rid of that? So there are two ways to do it, and I will discuss that in a minute. But I want to show you there's a reason to believe that we should go into the post-main sequence stage, because we can also use the same technique, try to measure alpha elements, especially C, N, and O. When you measure their element abundance, and there have been enormous amount of work on this subject, a lot of people have done this, and they measure it by looking at the line ratios. Now, when they do that, you have to interpret from the line ratio what is the actual metallicity, and in this AGN environment, you need to understand emission line physics, and including UV ionization sources. So people do a lot of this with the cloudy model. And after that is done, apply the cloudy model, and you find that there's these are low redshift AGNs, and these are redshift at 3 to 5, 2 to 5, and here are some redshift greater than 6 to 7. And basically, one finds that you can get into super solar metallicity at very early stages, and then they become roughly independent of redshift. And I will show some more evidence further down the line. And furthermore, you can do the averaging. You do the averaging, you look at the different elements like CN plus O, and you find that their metallicity is typically 3 to 4 times the mass, the value of the sun. And if you look at nitrogen relative to CNO, and nitrogen is very strongly enriched. And if you look at helium, helium is only slightly enriched. And iron is, in fact, iron to H ratio is slightly down from the solar value. So what do they tell you? So the alpha elements, 3 times solar, it tells you that the post-main sequence evolution must take place. And the reason for that is it's only in the post-main sequence evolution that you, through the triple alpha reaction and alpha chain reaction, you can cook them. Now, the nitrogen abundance being so high up, it means that the CNO was very important in redistributing the relative ratio between nitrogen and C plus O. And so there has to be more than one generation of stars. And the iron being slightly subsolar, it tells you that it is produced primarily from type 2 supernova, and all heavy elements in the broadline region, these are the broadline regions, the blue, are larger than the narrow line region. The narrow line region are produced further out where the capillary velocity is lower. And so it seems that there's some evidence of contamination in the region of the disk, in the broadline region, whereas the narrow line region is a supply. So how do you get rid of, how do you get these heavy elements cooked, and how do they come out? And the way you do it is to see if you can switch off the main sequence. So we ran some Mesa model with Muhammad Ali Dib and Andrew Cummins, and try to look at this problem. And what we find is that if the density of the background is relatively hot, relatively large, and then you tend to produce the forever stars. But if it's slightly less, and you can actually find that the star can evolve to some maximum mass and start to come down. And this once it gets down to relatively low values, it can evolve off the main sequence. And so why is this difference? And probably, and we are still getting to the bottom of it, is this question whether you have a radiative layer inside the star. And if you can establish a radiative layer inside the star, the fresh resupply of hydrogen does not get down to the region of the nuclear burning. So it does not really give you metabolism. It may merely pick up this material and then spilled out again. So, and that can actually cause, in the low mass case, the low density case versus the high density case. So the low density are produced from regions further out, or you can produce it in regions where you have a gap. So these are possible outcomes. The second way to limit the longevity of these massive stars is to limit the amount of material from the wind actually leaving from the immediate neighborhood of the disk. And because if there's a balance near lambda equals 1, really you have very little flow between in and out. And so you can get into a relatively static case. And if you're in 1D and it's stable equilibrium, you add a little bit more mass, and then the wind becomes a little stronger, and then it will shed off the mass. So there is a little oscillation. You can work out this oscillation amplitude. If it's relatively small, then the retention amount, whatever wind you generate, will not be able to get out. And if they don't get out, and then in this retention, and then the hydrogen fraction will gradually decrease in time, so much so like the blue line, and it will decrease in time, and eventually it will be exhausted, and the helium will increase, and then you will evolve off the main sequence. This is very similar to standalone stars, The only difference is that you have here accretion and wind going on at the same time. So as the molecular weight of the star increases, and their Eddington ratio also changes, and so if they're still in the fully radiation dominant region where you get an n equals 3 polytrope, and you find that in fact the mass will gradually go down as molecular weight go up, but when it gets into more convective stage, and the mass will go down even faster. So these two type of process tells you on the main sequence, not only you're accumulating more and more helium inside and you don't give out, and furthermore, that the mass of the individual star will gradually decrease, and the equilibrium mass will gradually decrease as they decrease. And this is where you started out with 0H main sequence. Here is terminal H main sequence. So you get down to about 30 or so solar masses. Now, why is this important? Okay, so the helium return is relatively modest, and the metal return is a few solar masses, and the remnants you'll produce is a few solar masses. So one can calculate these returns from the post-main sequence stage, and you produce, here is hydrogen and helium, and here you produce the various elements, C, N, and O. Notice that during the production stage, when you're producing C, N, O, N is much lower. That's because that's nuclear synthesis time. And but when you cook it again under C and O in the main sequence earlier phase, and during that phase, N can shoot way up because there's some bottleneck in the nuclear reaction rate. Okay. So reducing mass, getting down to about 20 or 30 solar masses, actually enhances the probability that you can produce supernova. Okay, and this is a calculation that was done by Woosley's group and also by Nomoto's group, and then they try to look at the probability. They study, under what condition you can get supernova, which will be 1, and what condition they would just get a core collapse. And that kind of scheme tells you that if the progenitor of the collapse at that point of collapse, if it is less than 30 or so solar masses, there's high chance of supernova, and otherwise they tend to collapse. So you can estimate the final byproduct of these objects. You can estimate the amount of heavy element you will produce. Now, these supernova are type 2 supernova, and they have a signature. And in the galactic chemical evolution, we know that the signature of type 2 supernova is in the iron over alpha line ratio. And when alpha elements is very low, and at -2, -1, or -2, and these are population 2 stars and dwarf galaxies, and you find that iron over alpha is subsolar. But when they start to get to high, more recent star formation, and the more recent star formation, they tend to produce more iron over alpha. That's because they're produced primarily from type 1a supernova. But type 1a supernova requires the formation of a white dwarf. And the formation of a white dwarf requires at least 80 million years. Now, some of these AGNs are observed at redshift of 7. So there's hardly enough time for these AGNs really to host the progenitor of white dwarfs and to produce type 1a supernova to give you the iron. So the fact that you see here, these are the byproduct of type 2 supernova is understandable. The difference with galactic chemical evolution is that this type of iron deficit is also associated with low metallicity, whereas here that we have high metallicity and low iron deficit. Okay, so these are the essential issues. And then you can compare narrow line region with broad line region, and this will give you more evidence of in situ formation. So there have been a lot of other work, and some of these work are I have not cited because there are some confusion over emission line physics. This is a thesis work, undergraduate thesis work by Xu Fei, and she's now a graduate student at Chicago, and her work shows that when she looked at these Sloan data and at different redshifts, all the way from 2 to 5, and for a given black hole mass, and she sees there's hardly any variation in the abundance. And so again, it tells you that the system is essentially a constant. Now, so not only you need to produce heavy elements very early, but you got to maintain at that level. And the reason you maintain that level, you remember I talked about the diffusion equation, is that you generate in the disk, and the heavy element the pollutant you return to is in that disk, and that disk still feeds the supermassive black hole because it feeds the supermassive black hole. So all of the pollutants that you get rid of actually get swallowed by the black hole, and this is the best way to get rid of the environmental hazard, and because they all flow down and there's no accumulation. So a supermassive black hole is the depository of these local heavy elements. And that sits well with what's going on. And what are the implications of type 2 supernova? And you produce different elements. But so this is what we were looking at in terms of these element gradient, abundance gradient. Okay, so I'm going to finish up very shortly, and because there, even though I haven't done half of it, because the other parts are equally exciting, but it would take too long. And so to summarize a bit, you know, the helium abundance is about less than 50%, higher than solar value, tells you that the helium production is limited and from the long-lived stars. And iron is less than the solar value. It tells you mostly produced from type 2 supernova and with a limited AGN duty cycle. And that there's no redshift dependence, tells you is a local contamination and local clearing. So the remnants, I would just briefly spend another 3 minutes to talk about the remnants. And the remnants are interesting because they are black holes and they can be trapped in the disk, and they can accrete from the disk. And then they can accrete in this region, and eventually they give the source. They become the source of gravitational wave emitters. And so you can produce multiple of these objects, and then they will merge. And but what is also interesting is how do you try to test this idea is by looking at the spin of the individual black holes. And these spin from gravitational waves, they can actually measure the spin, and usually the measured spin is very low. And if they accrete from the disk gas, would you not expect their spin to be high? But it turns out that these objects accrete from the turbulent disk, and these turbulent eddies will tend to give you spin reorientation and produce very low, what is called lambda effective. So, many interesting things happen around embedded black holes, and these objects, as they evolve and they grow, they are very much like planetesimals and protoplanetary embryos, and how they will grow, how they collide, how they merge, and how they eventually evolve. So I think I will probably stop there, and because I don't want to drag, I don't want to get into your lunchtime. Thank you. Maybe I can open up for questions.
Any questions or comments?
No, someone is
Koichi
is muted. Someone
He
else.
was not a second ago. I mean, I'm looking at the
Oh, okay. So anyone has a question? Okay, Doug, could I ask you a question?
Yes.
So I'm just wondering, you have this predictions of metallicity. So how do you really test it? So for example, do you really have grain condensed in the broadline region, and then you can actually see the trace of those elements?
They're a little bit further out of the broadline region is what is traditionally called dusty tori. And they have infrared access, and it's believed that the dust is presence is very prominent. And part of the reason that I'm thinking along that line, and as Paul knows that I'm crazy, always crazy, because I'm thinking that in fact, in these near these dusty tori, the metallicity being so high and all that, that it is actually a very favorable place to form planets. And there may in fact be planets formed around AGNs. And why do you want to speculate that if there's impossible for you to see it? And it may be that we are seeing something that is already there. For example, that around the galactic center, and there are these G clouds. And to understand exactly the origin of the G clouds and requires a considerable amount of construct. And so I think it is not inconceivable that the condition that we tend to associate with planetesimal formation in protostellar disks are really quite ripened around AGN disks.
Can I also ask, I don't know if you can hear me. So the expectation of the stellar population that us, I guess, whatever feeding or whatever that work with the black hole, around the black hole, presumably in principle there should be the lower mass versions should still exist around nearby dead AGN. And there you actually have a chance, presumably, of studying the population. I mean, we had an optical quasar, it may be hard to see anything, but there are plenty of dead black holes nearby, and we have from these, sigma relations, we kind of know at least the nearby inventory. But of course, these are the relative low mass ones. Is there something you'd be saying that metallicity you expect what? A very large metallicity gradient for the really nearby stars?
Yeah, so this is very interesting. And Paul will probably jump in to tell you that the nearest AGN is called SAGA. SAGA is a dormant galactic nuclei because there's not hardly any accretion onto it at all. But around SAGA, there's two populations. One is the S stars, one is the disk stars. They all have very similar age, namely several million years old. And maybe they all formed several million years ago at the same time. Is there any evidence? Is there any supporting evidence to suggest that there could have been an environment that hosted them? Well, there is. This is the Fermi bubble. You extract Fermi bubble back, and you get back to the disk around that time. So then what else can you learn from the S stars and the D stars? You can learn about their kinematics. And they have high eccentricity, some of them. And the eccentricity is not what you would expect from just simple, two-body relaxation or whatever, because they're very young. There hasn't been time for them to have. So you can do many of these type of dynamical analysis, and we try to do that. And so it's a gold mine. And the other related issue are the issues concerning that if you did form this number of stars, and as the disk gone away during the depletion of the disk, could you expect there could be some sort of a stimulus for these residual stars to undergo close encounters with a supermassive black hole? And if
are you saying that near a black hole you form no low mass stars? Because normally the majority of mass goes into low mass stars, and for every S star you see, there will be 100 solar G dwarfs. Somehow you're saying near black holes those never form, which is why we only see mass.
No, I didn't say
right?
they don't form. I said they form, but they will grow. Okay, their background environment is so fertile that you're not looking at a standalone star. You're inside this environment. The density is very high, even though the temperature, even though the sun speed is 10 kilometers per second, but the density is so much higher, 7 orders of magnitude larger than GMC. And then you are going to be in this environment. You can't help it but to grow. And when you're growing, the low mass stars will merge with the high mass star. You're just going to have what I would call iso heavy, namely single mass type of objects at any given radius. And different radius will have different masses. Now, then at the very end, the disk structure changes. And it takes about maybe a fraction of 10 to the 8 years to change. So a lot of these things do change. And I did leave behind this factor of F. This F is the, how much sub-Eddington you may be. And as they taper off, and you will produce some residual low mass stars. But it's not like the standard IMF that you would love and to apply to galaxy formations or whatever. It's because that what you started with a seed doesn't matter. It is the endpoint that matters, and they just want to grow, and they just want to grow. And that's why in the redwood forest, all of the redwoods are comparable in height.
So you're saying because it's so fertile, then there's no limit. There's no upper limit.
There will be ultimately there is a limit. That is when you grow to be so high, then the nuclear burning becomes Eddington. Okay, and once you start to become Eddington, you quench accretion. You also generate winds. And this is where you get to the equilibrium mass, is when the wind and the accretion balance with each other, you get into an equilibrium mass. That's why there's a ceiling. There's always a glass ceiling. So otherwise they will grow to 1 million solar mass. And so they will stop.
Anyone else has a question?
Thank you very much for your exciting talk. And well, I consider your research or this talk is pretty general in the sense that the conclusion has weak dependence on the accretion rate because you consider the star formation in the outer region of the accretion disk. However, for instance, for radio galaxies, except for radio loud quasars, the accretion rate is much less than the Eddington limit in the inner regions. In such a case, the inner region becomes either advection dominated accretion flow rather than circular snaps or knockoffs on the standard disk. Well, do you expect any important change of important conclusions if the inner region becomes enough in your argument?
I really like your question. And I think the reason I focus primarily on the very bright quasars is because we have all these spectra. And you can determine abundance, you can determine all of this. And it was also actually motivated because I was originally motivated by trying to explain whether this population is the dominant population of gravitational wave sources. And but as you're absolutely right, that most of the galaxies, they're not in the AGN phase, they're in the DGN phase, or they're in the faint phase. And if you do that, then star formation does not play a role. And because you get a phase transition and it's no longer self-regulated. And in fact, how do you make a transition from AGN to DGN? I think it is when you build up sufficient number of residual black holes. And when you build up these residual black holes, and then they accrete and they produce a lot of luminosity, and their formation rate is not self-limited. And they're only limited by the number of progenitor stars. So they can, once they form, they can still accrete. They don't go away. And like stars, and they evolve off the main sequence, of the post-main sequence. So all of these things are important, but my focus on this talk has been primarily on the bright quasars and the lower mass objects, and the star formation is not likely to be an important factor.
Okay, thank you very much.
Thank you.
So anyone else like to have a question? So how about online audience? Did you see any people? Oh, okay, Ping Gao has raised his hand. Ping Gao.
Yes, Doug, a very nice talk. Yeah.
Thank you.
Yeah. So just curious, you start with the turbulent disk. So the Tumark value is about 1. And of course, you consider the feedback from the stars. And I'm just curious how this Q value evolves. As stars have feedbacks onto a turbulent disk, and the disk will becomes more laminar. It becomes less gravitational, unstable. So how does that affect the, what is this model? You
Okay.
consider the turbulence, but suppose the turbulence can also help to accrete the gas onto the star spawn in the disk. Also a migration, right? Migration of these newborn stars in the disk. Also the turbulence plays a role, but the feedback's coming, coming out, and then actually make the disk a little bit calm.
Yeah, okay. I'm glad you asked that question. I think the beauty of this scenario is self-regulation. So as I said before, that if you look at these disks, if they become calm, you can still calculate the energy loss from the surface. It is so fast that the disk want to the viscous dissipation, as in normal circumstance, is not adequate to provide sufficient amount of heating to puff up the disk. So if the disk contracts in height and the gravitational stability becomes stability parameter, Q becomes less than 1. So you cannot have a disk which is laminar and Q much less than 1. So they would either, fragment to form new stars, or they can become, incredibly thin, give you a global scale spiral density wave, which is unlikely to happen. And so it is a self-regulated process. The moment you switch off, you have star formation, and with some feedback, yes, you will heat up, and then the Q value will increase. Okay, but then you stop star formation. So the stars that you form will evolve off the main sequence. And then that energy source is gone. When that energy source is gone, the disk becomes, it doesn't have adequate heat source. So it will cool and contract. And then the Q value will go way down. And then so it percolates around this region. Now, you also raise the issue about migration. And you also raise the issue about whether turbulence can promote accretion. Now, both these two problems are related. When you have turbulence in the background, or even laminar flow in the background, and then generally they can introduce spin reorientation, because the size of the turbulence and eddies are comparable to their boundary radius. So you can actually have the spin orientation of the material you accrete also fluctuates. And that's what produces the low chi effective observed in the merging black holes. And do they migrate? Probably, but not as efficient as you think, because the most migration calculations are done with isolated single planet at a time. When you have the coexistence of several hundred of these objects and in a turbulent environment, and their migration is quite complex. They will form small clusters. They will form binaries, they'll form small clusters, and then their evolution will start to play a very interesting role, because there are all kinds of secular dynamics occurs within those systems, and we're looking into that. It's a gold mine. It's a rich field.
Thank you very much. Yeah.
Anyone else? Anyone wants to have any further questions?
I welcome collaborators. There's plenty of problems to work on.
So another question for you, Doug. How do you distinguish planets that's formed in the earlier real protoplanetary disks and planets formed out of your new scenario?
I don't know. I think it's actually very difficult to observe them, if they can be. I've been scratching my head, see how they can be observed, and it's probably very difficult. But maybe there are plenty of if one day you observe some very high velocity planets, and that could be something that is produced from such a mechanism. And there's also the possibility of, during the DG dormant phase, that the individual black holes may capture some planets and accrete them. So they may have some signatures, but that's sheer speculation. I have no idea. I'm
Okay.
kind of primarily focused on G clouds.
So anyone else? So maybe, yeah, so that's so, well, it's getting late on your side. So then definitely this is a very stimulating talk, and we are raised to different level imagination. So yeah, so anyone who has further questions about plant information in different locations, welcome to ask Doug further. So anyone more? Minkai, you seem to have your microphone out.
Oh, sorry. I have no questions. Thanks for the talk.
Thank you.
He doesn't have a question, right? Yeah. Okay. So I guess we'll, Doug, thank you. I think we'll finish the meeting today, and then you could stop recording.
Okay.
And please